Welcome. In this tutorial we will show you how to take a CAD model, in this case it's a crane, and prepare that with dynamic simulation inside of Algoryx Momentum, which is a plugin for SpaceClaim. This plugin will help you to separate the CAD model into moving parts so that you get individual rigid bodies with constraints that allows for dynamic motion. Algoryx Momentum allow you to set materials and mass properties and all things, and everything can be exported into Unity. And by using the AGXUnity plugin, you can continue to model the scenario using wires and other things. So first we need to find the structure of this CAD model and to separate which are the moving parts, which are the individual moving parts. Next we need to activate the plugin, and this will create one single rigid body. And we can display that by pressing the Dynamics color button, and we will see that it's just one single rigid body. So we need to start to split this up into separate moving parts. So we start by selecting this crane hook and just split that. So then we'll get a number of separate rigid bodies. So now we have to find out which are supposed to belong to each other. So we see that we have a sheave construction, this circular object, and that should belong to the green axis that go through the system. So we will merge those two. And now they belong to the single body. The same thing here for the crane hook and this bolt, that should also belong to the same body. So we use the merge tool to merge them together. What we also can do is that we can group bodies together, and that will create a more logical structure. It will be easier to navigate in the model later on. So we'll create a new group and call it hook. And now we have 4 bodies belonging to this group. But we also see that there is one body here which are not going to be one separate body. So we need to merge that into the sheave construction, the cylindrical part here. So we just select those two and press merge, and then they are merged into one single body. So now we have 3 rigid bodies, which builds up the construction of the whole hook. So let's move to the rest of the crane. And I have speeded up this process a little bit so that it doesn't take too long time. But basically what we do is that we split them into separate parts, and then we merge them together to get one solid rigid body for the base, one for the overall boom arm, and also for the cylinder that are supposed to lift this construction. And at the end we will also have the sheave cylinder. But basically we use the merge and split tool to go through the CAD model and to put all the bodies that are supposed to be moving together into single rigid bodies. Depending on the structure of the CAD model, it can sometimes be a very easy process, but in this case we can see that the CAD model is a very flat structure, which means that there is no inherent information about moving parts. So we need to identify the moving parts one by one and merging them together. We can see that we use the merge tool, which is a very efficient tool because it allows you to see the individual rigid bodies based on the color. So you can control click on one shape and then click on another, and the first one will be merged with the second. It's also a good idea to go through the list of bodies so that you can identify if there's objects inside which are hidden by other objects, but they can cause problems, because if they are belonging to a separate body, then you get contact and they will sort of cause instability in the simulation, or it could jam the simulation. So it's important to get all the rigid bodies to be correctly structured. It's also a good idea to name the bodies, because later on we will find these bodies inside of Unity. So if they have a good descriptive name, it's much easier to continue the modeling inside of Unity afterwards. So as you can see here, we're naming the bodies so that we can get an understanding of what they belong to later on. Now when we're done separating moving parts into rigid bodies, we can go to the next step, and that's about creating joints. This is a jointed system, and there will be hinge joints, that is rotational joints. So for example, this cylinder here is supposed to have a cylindrical joint around its axis. So we use the hinge tool to create this joint. So we can see that we get a rotation axis around this center line. And there are many ways of creating joints in Algoryx Momentum. There's also a tool called detect joints. And detect joints will go through the model and try to find peg-in-a-hole systems, where you have a pin and a hole, and within some threshold it will try to recognize to see if there is supposed to be a joint. So we can go through each of these detected joints. They're still not joints. We have to select a type for each and every one of them. And in most cases, these are rotational hinge joints. But in one case here, the one selected, we want it to be a prismatic or a sliding joint. So we'll choose the sliding joint or the prismatic joint type, and we go through each of the other joints and just determine that it's going to be a rotational joint for each and every one of them. So even for the sheave, we can see that there is also a detected joint, which is a hinge. And down here at the hook, we can see that it only recognized one of them. It's for the sheave, but it didn't recognize any joint for the hook. And that's probably because there is a very tight threshold here. So there's no, it was not possible for the system to detect that it's a peg in a hole. So we need to manually create a hinge joint by selecting each part and creating it with a hinge tool. What we're also going to do is that we're going to select the prismatic joint, and we're going to set some properties, because this joint is supposed to lift the whole crane up. So we need to assign some reasonable force limit so that it's strong enough to lift this construction. And in this case, we set it to minus 50,000 Newton and 50,000 Newton. That is the amount of force for lifting and for lowering. In this case, we also enable the motor and the speed is set to 100 millimeters per second. And if we make the base a static, meaning that it doesn't fall in gravity, we can start the simulation and see what happens. What we'll notice is that the hook construction will just fall in gravity, because right now there is nothing holding it up. So if we start simulation, we'll see what happens. We can see that the crane arm is moving up because the prismatic motor is expanding with 100 millimeters per second, exactly like we wanted. But we set the speed to 0 before we continue. Also, we set the base back to dynamic, because we want that inside of our Unity simulation. To get a solid and robust simulation, we also need to model the sheaves as cylinder primitives. These are the primitives or the collision geometries that the wire will have continuous contact with. So we will route the wire over these cylinders. So we can design a new primitive, by using the design tools available in SpaceClaim. So we create the design plane and we just rotate the camera so that the camera is orthogonal to the design grid. We use the C keyboard shortcut to create the circle, and creating a circle with a specified radius according to the original triangle mesh. And then we use the pull tool to extrude this circle into a solid cylinder. And it should have the same width as the original triangle mesh. So we will move this primitive so that it's aligned with the original triangle mesh. And later I will show you how to disable collision with the tri-mesh and only have the collision available for the primitive, so that when the wire is colliding with the sheave, it's actually colliding with this cylinder primitive instead of the triangle mesh. And that will give you faster and more robust simulation. We can adjust the width by using this pull tool so that it's according to the original triangle mesh. Next, we need to move this into a new component, and that will also create a new rigid body. So we can either drag the component into the upper sheave, because we want those to be one single rigid body now. It has basically two representations. One should only be visual and one is for collision detection. So now we have one rigid body, and I will just rename this to upper sheave again. Having collision detection enabled for all the geometries is not very efficient. So what we do here is that we select all solids and we disable collision detection for all of them. So right now there is nothing in this model that will generate a contact. Next, we select the objects that we really want to have collision enabled for. So for example, this upper boom should be enabled. So we select that solid and we enable the collision again. That's where the wire will be routed, so we want contact with that. We also want this cylindrical shape that we just created for the sheave to be able to collide. So we select that and enable collision for it. So this means that when the wire is colliding with the sheave, it's only colliding with this primitive, and we can also give this solid a name, and that will pop up later in Unity, in the Unity hierarchy. What we also can do, we can set colors on objects so that they appear in Unity later with specified colors. In this case, we want to disable the rendering for the cylinder primitive. We also need to enable collision for the hook shape, and we also want to model a cylinder primitive for the sheave which is attached to the hook. So we do that in the same way we did for the upper sheave. We use the circle tool and then the pull tool, and then modifying it by moving it to the appropriate position and then moving it into the same rigid body, so that we get one solid rigid body with a cylinder primitive as the colliding object. We also want to enable the collision detection for this shape. We can also specify that the mass properties for the cylinder shape is not being taken into account. So the mass for the sheave, hook sheave, is only calculated from the volume of the original triangle mesh. To have full control over the contacts between different objects, it's important to create materials, physical materials. So we can select solid, one solid or many solids. In this case, we select the primitives for being used for the sheave, and we create a new material by going into the property window and entering sheave material. That will generate a new material which will be assigned to these cylinder shapes. We also set the simulation frequency to be the same that we're going to use inside of Unity. And the reason for that is that Algoryx Momentum will calculate damping for constraints depending on the simulation frequency. Now we can export this model into a .agx file. And this file will later be read into Unity. And it contains the whole simulation model that we just created. So inside of Unity, we find the deckcrane.agx, which we exported, and we import that into Unity using a feature available in AGXUnity. So when that is done, we also gonna create a ground plane, which is a rigid body, a box. So we can specify the size of that box by entering the half extents. So it will be 12 meters times 12 meters times 2 decimeters in height. We also want that to be a static, so it doesn't fall down. So now we have a ground onto which we will model everything else. Next, we pull in the crane prefab, which we just created. We position that into the scenario. If we would start the simulation now, you would have the crane hook falling down, colliding with the box, but also the crane would fall down. So we want to anchor this crane in the world, and we do that by creating a hinge constraint inside of Unity, so that this crane construction is connected to the ground box, and we align it so that it can rotate around its rotation axis of the base. We select the parent body, which is this box. So now we have a constraint which is attaching this crane construction to the ground. What we also do is that we enable the target speed controller and set the speed to 0 so that the crane doesn't start to rotate by itself. We will select this hinge and name it base hinge, because we're going to use it later to control the rotation of the crane. We will now create a new wire, and we will set some properties like the wire radius. In this case we use 0.07. We will set some resolution, and we can change that later on depending on what resolution we need. We're also going to add a script called wire renderer, so that when we render or when we simulate the wire, we will see the radius and the exact representation of it. One important thing is also that we need to create a material that we assign to this wire. And the reason is that we want to control the stiffness of the wire. In this case, the default bending stiffness is a little bit too high, which would result in a very stiff wire that doesn't want to bend. So we'll reduce that a little bit. We will assign this new material to the wire, and we just choose the new wire material. So when we now start creating a wire, it will use this newly created material. But to also have full control over the contact properties between the wire and the sheave, we will create a contact material. A contact material is something that defines what happens when two objects with specific material collides. So in this case we use the sheave material that we created in the Momentum and the wire material. And we're gonna set the restitution to 0, and we're gonna set the friction to some specific value, a little bit higher than default, but it's not really that important. So we set it to 0.7, and one of them is along the wire and the other one is orthogonal to the wire direction. So now we have the material specified between the sheave and the wire. We can now select the wire and start the routing procedure, and we do that by creating nodes. The first node we're going to create is a body fix node, which means that it will be attached to the shape or the body that I attach it to. So we get a node which we can translate relative to this attachment point, And we continue creating these nodes until we are done. The next node we're going to create is on the sheave, on the hook sheave, and it will be a free node. And a free node is something that will not be rigidly attached to a body. It will move in free space. It will be translated to contact nodes if needed. So we also need to make sure that we have some separation so that we don't model the wire inside of geometries, because that can result in a bad result. So we continue creating these nodes around the sheave so that it goes freely around and comes up on the other side, also with a free node. So we need to make sure that there is some space so that it's not going directly through the primitive. So we create another one, attach it to the side of the sheave. And the final one at the side of the sheave cylinder. And this will be the last one that is attached to this hook. And next we are going to route it in the same way over the upper sheave. The final node that we will create will be attached to this winch construction on top of the crane, and it will be a winch node. And this means that this node can be operated through the interface by specifying a speed and a force range. We can also specify how much wire is inside of the winch, so that when we start the simulation we can spool out some wire. A very important feature of AGX Dynamics is that we can assign a special property called pulley to a cylinder. So when we route a wire over that cylinder, it will try to maintain the contact between the wire and the cylinder so that the wire always goes over the center line of the cylinder. So this script extracts all the shapes from the children and adds a property pulley to that shape. And when the wire collider algorithm sees that property, it will always try to move the contact nodes of the wire to the center line of the baseline of this cylinder, so that it will be much more stable and it will be harder to move the wire sideways, which is perfect for this implementation of a sheave. So if we start the simulation, we can see the whole construction now. We can also notice that the wire is swinging a bit. So what we can also do, we can continue routing the wire and adding more nodes if we want to. So just for demonstration, I will show you that we can also create what we call an I node. An I node is a specific node which the wire has to go through, and the I node can be attached to a rigid body. So that if we create another node just before the winch, because the winch is the last one, so we just select the wire and we select the winch node, and then we say create a node before, and we select it to be an I node, and we specify that the parent is this crane boom. Then we can move this node to just about any point. And what it means is that the wire will now always have to go through that point. So we just have to move that so it's in some specific position relative to the crane. So if we now start the simulation, we will see that the wire doesn't swing so much on top of the crane. To control the crane, we will add the first simple version of the crane controller. And this controller will operate directly on the winch node. So it's called the winch controller. So we add that as a component, and if we look into that script, we can see that it has a code that extracts the wires as part of this component, but it takes the first one and extract the end winch, and we know that the winch was routed as last part of the wire, otherwise it would be the begin winch. So basically extract this winch and it sets a speed, and the speed comes from a public property that will be displayed in the user interface. So if we now start this simulation and we select the main wire, we see that this speed is exposed, and we can change it, and that will immediately change the speed of the winch. Moving forward, we will create a weight that will be lifted using this winch. So we just create a box of the default size, and we will create 4 wires, one from each corner, that will be attached to the crane hook. So we'll create the wire, and we will attach a body fix node, one for each wire at each corner. For each wire, we will also add one additional free node that will create some initial slack in the wire, so that they're not immediately being under tension, so they will fall down due to their own weight. It's important when you model a wire that you don't have the wire to penetrate the attached rigid body. So here we have a body fix node, and we have to make sure that the wire is not inside of this geometry, because that will create contacts which will try to push out the wire at the same time as it is attached rigidly using a body fix node. So we have to make sure that this wire is slightly outside. Otherwise you have to disable collision between the wire shape and this geometry. We have done the same thing for the hook here. We have just moved the attachment points slightly outside of the hook. We're gonna select the joint which holds the hook, and what we're gonna do is that we're gonna use the target speed controller and set the target speed to 0. And we're gonna set the force range to infinity, minus infinity to plus infinity, and also lower the compliance so that it's very soft. It means that this constraint will try to keep the hook from rotating, but it's not very strong. It basically is a friction that keeps the hook from rotating freely without any friction, which is unrealistic. To ensure the stability of the simulation, what we'll also do is that we will create inodes attached to the sheave, because we cannot just rely on the contact between the wire and this cylindrical shape. In some cases, especially when you spool out the wire can jump off the sheave. So to ensure that that doesn't happen, we will change two of the nodes to become inodes. And these inodes has a parent, and that will be the frame around the sheave, so that when the sheave moves, the wire will follow. But still, what will happen is that if you spool in and out, the sheave will continue to rotate because it still has the contacts on the bottom side of this cylinder. But these inodes will ensure that the wire doesn't jump off during simulation. We can now start the simulation and control the individual parts of this whole simulation. We can control the winch through the winch controller script, which is attached to the main wire. We can also control other parts of the simulation, such as the prismatic joint that can lift this construction up and down. We use the target speed controller and set the speed to positive or negative depending if we want to lift or lower the construction. We can also set the speed of the base hinge, which controls the rotation of the whole crane. But we want to create a better control script that exposes these properties in one editor setting. So let's construct such a control script. What we also need to do is to change the time step from the default 50 to, in this case, 60 Hz, so that it corresponds to the time step we had in Algoryx Momentum. Okay, so to control the whole crane, what we're going to do is that we're going to create a C# script that takes some properties and exposes some values which you can change to control the crane. So what we're going to do is that we select the deck crane, we add a component, and we have something called winch control. And it has a number of public properties here. So first we're gonna select a few constraints here. So for example, base hinge. We select the constraint named base hinge. The lift prismatic, well, we only have one prismatic here, and that's the one lifting this boom. And also the main wire, we're gonna attach that one like this. So let's have a look at this script. So basically we have these public properties which the user can set to control the speed of the winch, of the prismatic, and of the base hinge. There's also some properties here which are the constraints for the base hinge and for the prismatic, and also a reference to the main wire. And here are two properties that will be written by this script to indicate how much wire is being spooled in and how much tension is being applied by the winch. So the content of this script basically goes through and extracts a native implementation of the AGX Dynamics constraint for the winch and for the hinge and for the prismatic. So that's pretty basic. Next, what we do is that we set some range for the speed for the prismatic. So we clamp the value that the user has set to this range, and then we set the speed to the prismatic for lifting the whole boom. We do the same thing for the hinge. We have the user value, we clamp it to this range, and we set the speed to this hinge. For the winch, we're doing one more thing. We have the clamping of the value, we get the tension from the winch, get current force from the winch. We get the amount of wire being spooled in. And then we also do this, we just have a value of 16.3 meters. When the number of meters spooled into the winch exceeds this value, and we have a negative speed that is spooling in, then we set the speed of the winch to 0, so that it automatically stops winching in and don't try to pull everything into the winch. If we now start the simulation using this control script, we can access the winch, the prismatic lift, and the base hinge using this interface. We can also see the tension being applied by the winch to the wire. In this case, I've increased the mass of this load to 10,000 kilos, so it's a pretty heavy load. So I also had to adopt the force range in the prismatic joint. So to summarize, this tutorial has shown you how to take a CAD model, add dynamics inside of Algoryx Momentum plugin in SpaceClaim, exporting that into Unity, where we model the rest of the environment, including wire and winch. We also add a controller which allows you to set various properties onto the crane, so you can operate the whole crane construction. You can also add gamepad support if you want to, of course. I hope you learned a lot from this tutorial. If you have any questions, just email us at support@algoryx.se. Thank you very much.